Hello, everybody. My name is Nick Rivera. I'm a PhD student in the Department of Physics at MIT under the supervision of Professor Marin Suljacic. And today what I want to talk to you about is a proposal to bring free electron gain media to nanophotonics to realize new types of lasers in silicon platforms, in terahertz and infrared platforms, and so on. This is work that was done in collaboration with another PhD student at MIT, Shahrukh Khan, and also Professor Ido Kamener at the Technion. So the basic idea of this talk is bringing free electron lasers to nanophotonics. And so the picture that you should have in mind of a nanophotonic free electron laser is something like this. So I have a beam of input particles like electrons, and I'm going to treat them all classically. So they're coming in with some positions and velocities out of some kind of electron source like an electron gun, and they're incident on some resonance structure with some dielectric permittivity. And for this structure, you can imagine just a waveguide, a photonic crystal cavity, a ring resonator, a metal grating, you name it. These are all examples of structures that you can imagine. And these structures all have in common that they'll have some mode, which is phase matched to the electrons, that the electrons can then amplify through stimulated emission processes. And so the electrons pass through, there's stimulated amplification of this mode, and the electrons will come out as bunches spaced by the wavelength of the photon that they're amplifying. So what I want to show is that modern nanophotonic structures like hybrid waveguide resonator systems and also photonic crystal, like high quality factor photonic crystal resonances based, for example, on bound states in the continuum, offer new ways to realize these things in optics and give us opportunities for new light sources. In fact, one of the key claims is that the combined quality factors and mode volumes achievable in some of these systems allow the so-called threshold current, which is the beam current needed to get net gain, to be very low, on the order of nanoamperes, which can in principle be implemented in electron microscopes, such as scanning or transmission electron microscopes, provided that the electron can interact with the system for long enough. And that's exciting to me because it opens up a lot of potential applied opportunities for light sources. Electron-based light sources are naturally tunable. If you change the velocity of the electrons, you change the frequency that comes out. So that offers opportunities for tunable lasers. A lot of the platforms that we consider for phase match interactions with electrons involve silicon as the passive resonator structure. So you can imagine having a silicon-based source of laser light where the gain medium is actually free electrons propagating away from the silicon. The free electron gain media are quite versatile in the frequency ranges that they can operate at. So they can operate in the infrared and the terahertz at room temperature, and so that gives opportunities for new sources there as well. Beyond opportunities for light sources, there are also opportunities for new kinds of electron sources, because when the electrons come out of a free electron laser, they're organized periodically so that the electron density has a strong modulation at the wavelength that you're trying to emit at. So the electrons come out in periodic trains. So you can imagine that as the electrons come out of a nanophotonic free electron laser, you're left with a group of electrons spaced by 100 nanometers at a time. And these bunched electrons could then be used for other kinds of superradiant light sources for wavelengths comparable to the spacing of the electrons, like a UV superradiant light source. And also there might be applications for compact dielectric laser accelerators. Beyond that, there are also fundamental opportunities, and I may touch upon that at the end of the talk, but I wanted to include that here for parity. So now what I want to talk about is what a free electron laser is and how it works. So this schematic is meant to explain everything, really. So on the y-axis, I have the logarithm of the power in whatever mode I'm trying to amplify. And on the x-axis, I have the distance that the electron is propagated along the structure. Imagine that this structure is like a waveguide and you're measuring distance along the waveguide. That's if I'm operating it as an amplifier, but if I operate it as an oscillator, then you can imagine the x-axis to be time instead. So the idea is that the electrons coming from the gun naturally have random positions, which means they have random phases in the field that they're trying to emit. And that's because there are shot noise processes associated with electron guns. So these electrons, because they're phase matched to a mode in the structure, they can spontaneously emit a photon. But let's say that this spontaneously emitted photon has a wavelength lambda. Then this photon of wavelength lambda, by Lorentz forces, i.e. electric and magnetic forces, can modulate the trajectories of the electrons that emitted that photon. And the net result of that trajectory modulation is that the electrons will start to organize themselves into bunches spaced by the wavelength lambda. So there's a density modulation at wavelength lambda. And now when these electrons re-emit photons of wavelength lambda, they'll do so more efficiently. And the reason is that now part of the current density that this beam has actually has the same wavelength and therefore strong overlap with the photon you're trying to emit. And when this happens, they can emit more, they're emitting more strongly, and so they'll get modulated more strongly. And so that leads to a feedback loop where the kinetic energy exponentially drains into the electromagnetic field energy until saturation processes kick in, and you get these bunched electrons whose phases are now quite correlated instead of being random. So that's how it works. You have this resonant optical structure where the free electrons are both the gain medium and the pump. And now the question is why you want to do it. So in one word, I think the answer is versatility. In two more words, it's new opportunities. So the free electron laser principle, giving kinetic energy up to a field, is applicable throughout the full electromagnetic spectrum, because when you in free electron laser devices that currently exist, at other frequency ranges, you have electrons whose energies are on the order of tens of kilo electron volts, and therefore they can easily give their energy up as microwaves, infrared photons, visible photons, and even X-ray photons. And so this, of course, has a very long history. So there are microwave free electron lasers, and those are called things like traveling wave tubes and klystrons, and that dates back to work in the 40s, and these are still successfully used in radar and satellites. At the terahertz, there was some very interesting work 20 years ago, which serves as the inspiration for our work now, where a group from Dartmouth was able to get lasing into the infrared from electrons passing over a metallic grating structure. And of course, if you hear the phrase free electron laser, it's quite possible that the association you made was to X-ray free electron lasers, like the ones at Stanford in the European X-ray free electron laser, where they send ultra-relativistic electrons through bending magnets that alter their trajectories, undulating them back and forth, causing them to emit X-rays that then remodulate the beam and amplify the X-rays. So this principle also extends to X-ray frequencies, and people are interested in extending it even down to gamma ray frequencies. There's been a notable lack of activity in the infrared through the ultraviolet. So people haven't really explored making like a nanoscale infrared or optical laser based on free electron gain media. Part of that could be that that there are already lasers, but I think the new opportunities for, say, silicon light sources and tunable light sources motivate consideration of this kind of gain medium. So now we want to describe the problem of nanophotonic free electron lasers in more detail. What I want to show you is the theory that we developed in order to figure out what's needed to advance this kind of field. So we're describing our electron beam through a set of initial positions and velocities. They're classical billiard ball particles, and they move through this resonance structure with some known dielectric permittivity, which is inhomogeneous in space. And the question that you want to answer, given these initial conditions, is what is the final state of the particles, so their positions and velocities, and also the electric and magnetic fields associated with the output, either spontaneous or lasing fields. And this is a very general problem. I mean, this is described by the Maxwell equations coupled to a current, the current which is determined by the velocities and positions of the electrons, which are coupled to the electric and magnetic fields through the Newton-Lorentz equations of motion. And so typically people largely consider the simpler regimes of this, where either the particle trajectories don't change or the field doesn't change. But there's been a lot of interesting work in both of these areas in the context of nanophotonics. For example, in this one regime is where the particle trajectories don't change. You just assume that they move at constant velocity, and that's the spontaneous emission regime. And this has been explored a lot in the context of nanophotonic light sources based on free electrons that can be tunable and also implemented in silicon. And so the basic physics behind that is that you have some point charge which represents a moving current. That moving current is this moving delta function here, delta of z minus vt with velocity v. And if it emits something that has a plane wave component with wave vector k and frequency omega, then the work that that field does on the current is given by this integral over the electron's trajectory from 0 to the end of the structure of e to the ikz minus I omega z over v. And so if you want the energy in the field to grow linearly and not oscillate, then you want phase matching. You want the phase velocity of the photon, omega over k, to match the velocity of the electron v. And so examples of this are in Cherenkov radiation, where you have an electron moving faster than the speed of light in a homogeneous or homogenizable medium, which leads to a characteristic optical shock wave. But the other important example for this talk is Smith-Purcell radiation, where an electron moves above a grating and emits spontaneously into block modes of that grating. And the reason you have phase matching is because some of the lattice harmonics of that block mode have a phase velocity which matches that of the electron, which has been explored by some of our colleagues. So for example, what was explored was looking at bound states in the continuum and silicon gratings to enhance Smith-Purcell spontaneous radiation. In another case, what was looked at was silicon-based structures for silicon-based tunable light sources that in principle could one day be CMOS compatible. So another area of this general problem is where the fields don't change, but the electrons do. And that brings us to a long history in a field of dielectric laser accelerators, where you have some constant plane wave field in your structure, E naught cosine kz minus omega t, and the electrons accelerate in that field. And depending on their initial phase in the field, they either accelerate or decelerate. And so people implement this as follows. You have some kind of dielectric grating with a channel. The electrons move through the channel and then get either accelerated or decelerated by tens of kilo electron volts. And people are also exploring inverse design nanostructures for this kind of problem. But the free electron laser, the nanophotonic free electron laser problem differs from both of these. For example, free electron lasers operate by stimulated amplification, which is seeded by spontaneous emission. So it has both the parts of the nanophotonic light sources and the dielectric laser accelerators, because you can think of the spontaneous emission as the seed that gets stimulatedly emitted. So it basically combines both aspects of the problem. And because this problem is not generally solvable, we need a suite of methods to understand the problem, both semi-analytical methods and ab initio methods. So I want to describe what we've developed there. In terms of semi-analytical methods, what I want to show you now is a general description of nanophotonic free electron lasers that is pretty general in the sense that it captures all the quantities you would want in a classical laser theory. So you'd want to know things like what the gain is for different modes, what the thresholds are, what the saturation intensities are, if there's a steady state, and so on. And so this semi-analytic theory is quite general. If you know the modes that can laze and you know the initial phase space distribution of your electrons, you can really solve everything. So I want to show you a little bit of that. So the basic assumption, like in laser theory, is that your field is expandable in terms of a few lasing modes. So I'm assuming some multi-periodic state. So your E of R and T is a sum of resonances EM of R with time harmonic frequencies omega m, weighted by envelope functions that propagate in the direction parallel to the electron at group velocity Vg. And what I want to assume is that the gain is not so large that you have exponential gain over the scale of one wavelength of the photon. So I want to assume that there's a scale separation in the problem so that I can assume that my envelope is slowly varying. And for a lot of what I'll show you, that's quite perfectly valid. And so when that happens, I can divide my resonance structure into chunks that are large compared to the microscopic scale of the wavelength, but small compared to the scale of the gain length. And then I can look at a coarse grain system, and when I do that, I get a very simple equation for my envelope function. So on the one hand, on the left-hand side, I just have this envelope equation that propagates at the group velocity of the mode. And on the right-hand side, this is the influence of the electron beam on that mode through emission processes. And so what you see here is basically a sum over positions in each chunk of the electric field evaluated at the position of each electron. And so I want to give you some intuition for what this term is doing. So we can imagine some kind of field like e to the ikz. So this term E star is going to be e to the minus ikz sub I of t. And we can actually ignore these v's to understand what happens. So we basically have a sum over particles of e to the ikz I of t, which means it's an average phase of the electrons in each chunk. And this thing is called the bunching factor. So if the electrons are distributed according to random positions, and let's say you have n of these electrons, then this average phase is going to be something like 1 over square root of n. But if the electrons are perfectly distributed according to the wavelength of the photon, as I showed you in some of the earlier figures, then this bunching factor is 1. So we can simplify the equations quite a lot and think about gain and thresholds in the linear regime by introducing collective variables. So we can introduce a bunching factor, which is this average phase that I told you about. And then we can also introduce an average phase modulation, which is like the bunching factor, except it's also weighted by a detuning factor. It's the detuning of the electron's velocity from the phase velocity of the photon. So The field envelope couples to the bunching couples to this phase modulation, and the phase modulation couples to the field. So I have this set of three linear differential equations, and I can look for growing solutions in space for an amplifier and time for an oscillator. I will show you the spatial case. So the gain constant, it's on both sides. So this is an equation that's a third order. But this gain constant is a product of two essential factors. One is a spatial overlap between your electron beam density perpendicular to the direction of motion, which is encoded by the plasma frequency, multiplied by the mode profile also in that transverse plane. So there's an overlap between the density and the transverse field. And then there's also a momentum overlap factor. So on the numerator, I have the distribution function of the electrons in velocity space. And the denominator, I have a phase matching denominator. This is a small typo. This should be omega over Vz, but it peaks when omega over Vz is equal to k, when you have phase matching. So this is an overlap factor between the electron's velocity distribution and the phase matching condition. Okay, and so these kinds of things are what we'll use to evaluate gains and thresholds, and you can really apply this to any nanophotonic structure you like. You can apply this to all the modes of it to find out which modes will lase and when. So it's quite a useful in general theory. Another important class of methods that I just want to touch on briefly are so-called ab initio methods. And the idea behind ab initio methods is that you tell me the input particles, and you also tell me the permittivity profile of the resonance structure, and I'll tell you everything about the final state, the full phase space distribution in position and velocity space of the different electrons, and the output fields. And for the beam densities and beam parameters usually using optical free electron lasers, it is actually possible to track every single electron. So it is a feasible approach. And so to do this kind of thing, what I'm really saying is that you need to take some kind of black box time domain solver, like an FDTD solver, like what we did in MEEP, for example, and then also couple it to the Newton-Lorentz equations that follow the electrons as a function of time. So it's solving everything self-consistently. And there are a lot of benefits to an approach like this. You can handle things that the analytic or semi-analytic theories really have trouble with, like pulse systems that could give you the highest intensities, systems where you don't really know what mode will lase because there are too many options. It gives you exact insights into the nonlinearity and saturation of the system. And a particularly interesting thing in MEEP actually is that it's outfitted to do other things. Like we could think about something in MEEP where you could actually simulate regular two-level gain media coupled to these electron gain media and see coupled laser systems like this. So there's a lot of space for new first principles kind of stuff. And of course, I want to mention that there's a long history of ab initio approaches in traveling wave tubes and X-ray free electron lasers. Those are called particle and cell codes. And so really all I'm proposing here is to apply these to these nanophotonics problems. So now I want to show you what this looks like. I want to show you a few proposals for systems and what we can expect from them and how we might realize them. So the first proposal here is a kind of very low threshold free electron laser based on what I believe to be the ideal structure for realizing a nanophotonic free electron laser, which is called a racetrack resonator. These systems have been built, these racetrack resonator systems have been built before in the context of Brillouin lasers. They can have extremely high Q. And what they comprise of is basically two very long waveguides of length L, joined by bends. So it looks like you spliced a ring resonator and attached it to the ends of two parallel waveguides. And so now let's imagine that we have an electron beam traveling parallel to the long waveguide segment. Well, if the electrons move faster than the phase velocity of the waves in the waveguide, it can emit into them via Cherenkov radiation. And so we can figure out which kind of modes are emitted by a construction like this. We can draw the dispersion of all the waveguide modes in the system. Here I'm just showing 10 representative ones. And then what I need to do is I need to find the points where omega over k is equal to v, i.e. where the phase velocity of the photon matches that of the electron. So I can just draw a line starting from the origin whose slope is the electron's phase velocity, and then the intersections of that electron line with these photon lines will tell us the different kinds of modes that can lase. And you can see already here that there's something that looks like it might be undesirable, but it'll turn out to be okay. There are many options for what can lase. There are already 10 here, and so you might be worried that 10 different modes can lase. But actually, the electrons discriminate between different types of modes quite strongly, and so there will actually be regimes of current where there's only one mode lasing at a time. So in particular, the mode that the electrons would like to lase in most readily is this pink mode over here, which is mode number 7. Whose electric field, parallel to the electron's velocity, has a lot of it outside of the waveguide. And that's important because the electrons have to travel outside of the waveguide in the vacuum region. They can't travel through a solid structure. They will be stopped immediately. So now I want to show you is what kind of gain is available in that system for that kind of mode number 7, whose electric field parallel to the electrons is outside the waveguide. So here what I'm showing you is the gain rate, assuming operation as an oscillator, as a function of the electron's velocity normalized to the phase velocity of the photon. So here the electron's moving 1% faster than the photon phase velocity, and here it's moving 1% slower. And I'm showing this for different lengths of the waveguide part, so 50, 100, and 250 microns. And I'm imagining a beam current of 1 microamp and a beam radius of 100 nanometers, which is in principle possible in Schottky field emission sources. So what you see is that the gain is much stronger when the interaction length is longer. There's no surprise. It's quadratic, so the gain for a 250 micron interaction is 25 times longer than for a 50 micron interaction. The gain rate that you can imagine here is something like 10 to the 10 inverse seconds. That means that the gain quality factor is on the order of 10 to the 5, which means that if your Q is over 10 to the 5, then you can get lasing. And another important thing I want to mention, you can already see it here, but the electrons need to move ever so slightly faster than the phase velocity of the photon in order to get net gain. If they move slightly slower, then you get net loss, and you're accelerating the electrons through like a particle accelerating type mechanism. So then the question is, well, I know the gain, so what are the thresholds for the individual modes? So assuming a quality factor uniformly of 10 to the 6 for the different modes, of course, that's questionable, but let's just assume that for a second. Then the threshold currents, i.e. the beam currents needed to get net gain, are shown here. So I'm showing the gain as a function of the transverse mode number from 1 to 10. And you can see that for any of the interaction lengths, this mode number 7 has the lowest threshold by an order of magnitude, which means there's an order of magnitude region in current space where this mode is the only thing that will lase, and there's not competition with many modes and deleterious multimodal effects. The other thing I want to point out in this figure, though, is actually the magnitude on the y-axis. The threshold here is something on the order of 20 nanoamperes. And that's 4 orders of magnitude lower than anything reported for the closest system, which is this terahertz free electron laser. And a lot of that is coming from the fact that this system is operating at high Q. If it had a much lower Q, like 100 or 1,000, the threshold current would be something like tens or maybe even 100 microamps, which is closer to this terahertz system. So these high Q structures really, really matter. I want to show another example, which is just based on a high Q photonic crystal resonance. So we can imagine that we have some kind of silicon on silicon dioxide grating. So the grating is made out of silicon, and I have electrons flying over that. And let's just assume it's a one-dimensional grating. And let's say that like this kind of structure actually supports high Q resonances at the gamma point of the Brillouin zone. It does that through a mechanism which is bound state in the continuum, where the outgoing waves normally are actually decoupled by symmetry from the far field, and so the radiative losses are very low. And this was explored by my colleagues in the context of spontaneous Smith-Purcell to enhance them. So I'm going to breeze through this part very quickly because it mostly corroborates what I showed in the previous slide. But if you look at the thresholds for this kind of system, if you have a quality factor on the order of tens of thousands, then your threshold current is on the order of like tens of microamps. While if you have a quality factor of like 100,000 or so, which was recently achieved by topological merging of bound states in the continuum, then you can get threshold currents, which are on the order of tens of nanoamperes again. So it's significant for the same reason. And here I'm showing the nonlinear dynamics, but I'll show that again right here. So I also want to show you what this looks like when you simulate this kind of structure through the ab initio approach. So here I'm imagining I have the same silicon waveguide. I'm pumping 100 microamps of current through it. In practice, this is something like 15,000 electrons. 45,000 electrons over 1,500 optical cycles. And what I'm showing you here is the electric field parallel to the electron's motion as a function of position for the last 15 periods of this grating, which is 250 periods. The period of the grating is assumed to be 500 nanometers. So what you see is that inside the like blocks of the grating, there's one particular mode which is excited, and that's the same mode that's actually the bound state in the continuum mode at the gamma point, and you can see that it's quite near the gamma point as the radiation is quite normal to the grating. The other thing I want to point your attention to is actually the magnitude of the saturation field, which is something like 6 × 10⁷ volts per meter, which is like tens of megawatts per squared centimeter. So it is a considerable intensity that you can get from these systems. And then I also want to show you the particle dynamics that you can imagine from this kind of ab initio code. Here I'm showing all of the electrons in the 250 period grating region. And what you see is that when the electrons enter the grating, they mostly have all the same velocities. which is the velocity needed to couple to this bouncing in the continuum in a nearly phase-matched way. But as they propagate along the grating, the electrons spread out in velocity. Some accelerate and some decelerate, and that's no surprise. The deceleration is stimulated emission, and the acceleration is absorption. But there's much more stimulated emission than absorption, which tracks with the idea that there's net gain. And so if you zoom in on the particle distribution in the last 10 periods of the grating, what you see is that the electrons are almost perfectly distributed by the period of the grating A, which is the wavelength of the first Bloch harmonic. So you can see many of these phenomena of stimulated emission and bunching are actually quite possible when you send electrons through photonic crystal structures. So these collective effects could be a possibility. And finally, I just want to comment on potential realizations. So the parameters realized for both needed for the electron beams as well as the photon are realizable individually. Schottky field emission sources realize the currents that I need, while racetrack resonators and other photonic crystals with high Q BICs also realize the quality factors needed. The difficulty is actually sustaining a long enough phase match interaction for the electrons to interact, to have this 250 microns. But there's been some quite promising work in this regard by my colleague Ido Kaminer, and I'd like to point you to his talk where he explains this on Friday at 8 a.m. So I'm quite optimistic about this. I think there's a rich space for applications and fundamentals, and I'm excited to keep working on this and to collaborate with people in developing this field further. And so with that, I thank you for your attention, and I just want to thank my collaborators and advertise some talks. Thank you.